Welcome to Spring LIB.
In this exercise, you have a conveyor belt that is moving with a speed of 4 meters per second, and on top of the conveyor belt and at rest relative to the conveyor belt, there is a block that has a mass of 15 kilograms, and the coefficient of static friction between the conveyor belt and the block is equal to 0.8. And our goal is to find what is the shortest amount of time, t, that the conveyor belt can take in order to stop, to completely stop, that is to go from the initial speed v0 of 4 meters per second to a final speed v of 0 meters per second, so that the block will not slide in the conveyor belt. In order to do that, notice that the acceleration of the belt as it's slowing down is equal to the variation in speed divided by the time it takes for the belt to stop. So if we're looking for the shortest time, so the smallest possible time, we are actually looking for the greatest possible acceleration. So actually what we're going to look for here is what is the greatest acceleration that the belt can have so that the block does not slide. Okay, so in order to solve this exercise, we need to draw the force diagram on the block. So here we have the block. The forces that act on the block are the gravitational force that acts downwards. We also have a friction force that's pointing opposite to the direction of imminent movement of the block. This is the friction force. Okay. And basically, we can decompose these two forces in two components. One component that I'm going to call y is perpendicular to the block, and the other component is parallel to the surface, and I'm going to call it x. The gravitational force in the x direction is equal to minus mg sine theta, where theta is the angle that the conveyor belt does with the horizontal. So it's this angle here, okay, which according to the exercise is equal to 30 degrees. So let me draw it here. This angle is 30 degrees. And then, besides the gravitational force, we also have the frictional force, Ff, and this is equal to the mass of the block times the acceleration of the block. And in the y direction, we have the y component of the gravitational force, which is minus mg cosine theta plus the normal force that the surface exerts on the block. So this is the normal force. I've forgotten to write here. This is equal to 0 since the block is not moving in the y direction. So from the second equation, we get that the normal force is mg times cosine theta. And we have that the maximum frictional force that can act on the block so that the block does not slide is equal to the coefficient of static friction times the normal force. So it's mu s times mg cosine theta. So if we substitute this into the equation for the x component, we have minus mg sine theta plus omega s mg cosine theta is equal to the mass times the acceleration. So the masses cancel out. So we get the acceleration. And notice that the acceleration here is pointing upwards. That's exactly what we want, since the block is moving downwards originally, and we want it to stop moving completely. So we want the acceleration to be pointing upwards. This means that the acceleration that we're going to use is positive, okay, because the acceleration is pointing upwards, and we're considering in our calculation that the acceleration is pointing upwards. So A is g times mu s times cosine of theta minus sine of theta. Okay. Then we can substitute the numbers. We have that A is equal to 9.8 meters per second squared times mu s, which is 0.8, times the cosine of 30 minus the sine of 30. So A is equal to 1.89 meters per second squared. So this is the acceleration, the maximum acceleration, and now we can find what is the minimum time it can take for the conveyor belt to stop. So know that the acceleration is equal to delta v divided by t. Now the acceleration is positive, meaning that it's pointing upwards. Okay, so delta v is positive. So we have 1.89 meters per second squared is equal to 4 meters per second. That's the magnitude of the difference in speed divided by t. So t is equal to 4 divided by 1.89 seconds, and this is 2.11 seconds, which is the answer to our exercise.